Alright, so number 4 is saying find the area between the loops, and so if we look at our chart, between the loops is find where you first visit the pole, then subtract the region from the consecutive zeros. So it sounds complicated, but here's like what you're supposed to do. So find the zeros of the function, so you'll get 0 is equal to 1 plus 2 cosine theta. So negative 1/2 is equal to cosine theta. So theta is equal to 2 pi over 3 and 4 pi over 3. Now, when I say find where you first visit the pole, I just mean the smaller angle, because the smaller angle is where you're going to visit the pole first. So if we were to graph this function, it would look something like, well, if we set theta equal to 0, cosine of 0 is 1, times 2 is 2, plus 1 is 3. And it would look something like this. So actually that's not a good drawing because it doesn't, like, there. So that's what it would look like. So when we're traveling along, the first place where we would visit the pole would be here at 2 pi over 3. So that's where I first visit the pole. And so what I'm going to do is these regions are symmetrical, the top and the bottom, even though they don't look like it because I drew it so sloppily, but this top region is symmetrical to this bottom region over here. So if I can do 1/2 times the integration from 0, the angle 0, to that spot of 2 pi over 3 where I first touched back at the pole, because I remember I want, between the loops, I want all of the red area without that little inner region right there. So, like, I want everything except for this, okay? I go from 1/2 to the first time I hit the pole, so from 0 to 2 pi over 3 of the function, squared d theta, subtract, and I'm going to multiply that by 2, by the way, because that this by itself, just the without the 1/2, this will give me the area of the top. But the top is symmetrical with the bottom, so I need twice of that. And so I have 2 times 1/2 the integration from 0 to the first time I hit the pole of the radius squared d theta minus, now I need 1/2 the integration of something, which is going to be the function squared d theta. And this is where I find my other limits of integration. So, and then it says right here, then subtract the region from the consecutive zeros. So here are my consecutive zeros. Subtract this region from the consecutive zeros. So my consecutive zeros are 2 pi over 3 to 4 pi over 3. And if you think about it, from 2 pi over 3, if I'm like highlighting this with green, 2 pi over 3, I'm here, and then I go around to 4 pi over 3. And so that's the area of the inner loop. So that's what I'm subtracting when I say the subtract the region of the inner loop. So then I can simplify here and plug it into my calculator, and that's what I should get. For number 5, inside outside, so I'm going to need the washer method. So I'm going to sketch my functions and then figure out which one is the big R and which one's the small r. So 3 cosine theta, that's just going to be the circle with the radius of 3. So this is 3 cosine theta, and then the other one, 2 minus cosine theta, is going to be here it's going to look something like this. So we want inside r's, so this is 2 minus cosine theta, and this is 3 cosine theta. So I want the area inside the red but outside the green. So this is what I want. So what I'm going to do is, if I look at just what's happening in the first quadrant close up, I have the green coming in, then the red over here, but I want just this region right here. So it's coming in, I want just this region right here. I need to find my points of intersection first to figure out where this point is. So I get 3 cosine theta is equal to 2 minus cosine theta. And so this will give me 4 cosine theta is equal to 2. So cosine of theta will be 1/2. So theta will be pi over 3 and 5 pi over 3. Which makes sense because this would be theta is equal to 5 pi, or sorry, pi over 3. And I'm going to actually change 5 pi over 3 to negative pi over 3 just to show you that it's symmetrical. Like, you don't have to change it, but I want to show you that this region is symmetrical with this region. So once I find my points of intersection, I know that this is pi over 3. And then now to find the inside-outside, I'm going to sweep from the origin. So whatever I touch first, and when you sweep, you have to sweep so that you'll eventually, your arrow will eventually come into this region. So you can't sweep here because you're not going to touch the region that you want. So I'm going to start here. So the first region I touch is 2 minus cosine theta, and that tells me that 2 minus cosine theta is going to be my small r. And the second region that I touch is the 3 cosine theta, which tells me that that's going to be my big R. So you remember, you can't sweep here. You have to sweep where you touch the area. So this is going to be the 1/2 the integration from 0 to pi over 3, from 0 to the point of intersection, so 0 to here, because that's where all the area is, of the big R squared minus the small r squared d theta. I'm going to multiply that by 2, and that will get my answer. Because that is just this, and I need to double it to get that. And then I'll do this one really... Well, yeah, I'll do it in a separate video.